So this is the equation, now we get it, right? ln of pi I divided by 1 minus pi I is equal to minus 4.372, which is my intercept, plus 0.067, which is my coefficient, into age, which is my independent variable. Now how to decode this relationship, we will move on. Now this is the data set that we have used, right? There are 20 rows, which is sample size is 20. Age, which is your independent variable, is given x, right? And then this is your dependent variable y. It can take a value of 0 and 1. 0 means there is no disease, and then 1 means there is a disease, right? So these are the two columns that we will be inputting to any software, right? So obviously the dependent values are 1, 0 and 1, and then out of which what essentially we try to get what is called as predicted probability, which is your fourth column, right? So how do we get 0.06308 is the understanding we need to have. Now if you look at it, so this is your LHS, which is a probability we referred as pi of x, and this is your sigmoid function. Now alpha and beta value we got from the previous equation. Alpha is nothing but your intercept minus 4.372, right? So alpha is equal to minus 4.372, and your beta, which is your beta coefficient, is equal to 0.067, right? Substituting the values, what do we get for different values of age, right? So from 25 till 84, so we keep on substituting, right? So this is, if you see, this is 25, if you see, this is 84, right? And all the values in between. So all the values of age is being substituted here and also here, and then alpha and beta values are plugged in. When I get it, this is the equation I get, right? So this is a nice curved line I get, and for that I get the respective probability. So when I substitute and solve for this, I get the respective probability value, right? So as you can see, it also establishes a relationship between the age and probability. As the age increases, you can clearly see, as the age increases, probability of the disease also increases. Now the output of logistic regression is a probability, but essentially what we want whether it is a 0 or 1. How do we do? Then we decide something like a cutoff probability, right? So we decide a cutoff value for the probability. Who decides that? The researcher decides it, right? So in this case, if you look at it, 0 up to 0.44 they have taken, and then 1 is 0.5. So that means 0.5 and above, that is greater than 0.5, they have classified as 1. Less than or equal to 0.5, they have classified as 0. That is, probability is more than 50%, then I classified as 1. Probability less than or equal to 0.5, that is 50%, I classified as 0. Now if you look at it, the third column is the actual one and the fourth column is the predicted one. Now what is the similarity or the difference between the third column and fifth column is what I will compare, right? Whether my predicted class is matching exactly with the actual class or not. If it is matching exactly, then it is a great equation that I have got it. If it is not matching, usually misclassification occurs, then how much of accuracy it gets, right? So if you look at it, these two are misclassified, right? So the actual class is 1, whereas predicted probability is 0.19, and hence it is classified as 0. Now if you look at this, this is 1 and this is classified as 0, and this is 1, likewise this 0 is classified as 1 here, then 0 is classified as 1. So that means here 2, this is 3, this is 4, this is 5. So out of 20, 5 are misclassified. So the accuracy is 15 by 20. So that means 75% accuracy. my model is 75% accuracy, because 15 classes are classified correctly and 5 classes are misclassified. So the accuracy of my model is 75%, right? Now this is one way to understand the predicted probability. Now let me explain how this exactly 0.063 is done. So this is the equation. So take for example the first sample. Let us try to delve deep on how this 0.063 comes. Now this is the equation. I put in the alpha value, I put in the beta value, I put in the x value. X value is this, right? And this is your beta alpha value. This is your alpha value and this is your beta value. So plug in all those stuff, that is exponential of alpha plus beta into age. So age I put it in 25, then I get the value of this after calculation, which is your numerator part, and denominator part 1 plus the exponential part, I get this denominator. The numerator by denominator, I get a predicted probability of this. So you can verify it. So this is how the predicted probability we get it. Now we have understood the relationship between the dependent variable, which is natural logarithm of odds, and how it is written in the equation format in the from the output, and also we have seen about the how to calculate the predicted probability. Now how to interpret the relationship between the dependent variable and independent variable. In this case dependent variable is the disease and independent variable is your age, right? So if you look at it here, ln of pi I divided by 1 minus pi I is written like this. Now I am going to ignore the intercept for some time and then concentrate only on age. Now ln of pi I divided by 1 minus pi I is equal to 0.067 into age, but when if I want to drop the ln, then I need to take a natural logarithm, then and hence it becomes pi I divided by 1 minus pi I is equal to exponential of 0.067, which amounts to 1.069, so on and so forth. Now pi I divided by 1 minus pi I is nothing but odds. How to understand the relationship? This is if ln of pi I divided by 1 minus pi I increases by 0.067, which is your 0.067, that means p divided by 1 minus p1, that is pi I divided by 1 minus pi I, right? So pi I divided by 1 minus pi I will increase by exponential of 0.067, which is becomes 1.07. So now this 1.07 how to interpret? That is 1 unit change in age, that means 1.07 into age will come here, right? So 1 unit change in age will increase the odds. What is this? This is odds. Will increase the odds of getting disease by 7%, right? That is 1.07, and hence it is increases the odds by 7%. Let us say two examples. If it is 1.07, it increases the odds by 7%, increases by 7%. What happens if it is 0.67? Now it decreases the odds by how much percent? 0.33%, 0.33, which is 33%, right? So this is how you need to understand relationship between the odds and the independent variable, right? So in the next class we will try to dwell deep into further understanding of interpretation of the parameters in logistic regression.